Why'd you die? Hey everybody, welcome back to Gideon Stuff. So today we have a little bit of a different video. A lot of you have been requesting that I do some more geology or paleontology content, and I think that's a great idea. It's something I love, obviously. I'm making a career out of it. So yeah, let's do some of that on this channel. And don't worry, never fear, the knife stuff isn't going anywhere. We're still going to be doing that. But yeah, every once in a while, I'll throw a geology or paleontology video down. Let me know if you guys enjoy it. So, what are we talking about today? Holy cow, I need a little bit of a trim. Oh well, it's a couple of days after Christmas. I'm still just relaxing. Anyways, today we're talking about the extinction of the dinosaurs. And this is a topic that's kind of near and dear to me right now, not just because dinosaurs are awesome, but because I actually did a lot of research and wrote a paper on this very thing last semester. So, yeah, it's something that I really enjoy talking about. So, before we get into what killed dinosaurs, let's talk about extinction events. A mass extinction is any event that leads to a large population of animals dying out at the same time or pretty close. The Earth has undergone several mass extinctions, the largest of which was the Permian mass extinction. And the dinosaurs have actually survived a mass extinction. At the end of the Triassic period, there was an extinction event that killed a lot of the world's critters, but the dinosaurs pulled through, and actually that extinction was the best thing that could have happened to them, because not only did they survive, but going into the Jurassic period, they proliferated like crazy. They diversified and they took over the world. In the Triassic, dinosaurs were kind of small, and in the background, other animals were much more successful, much more diverse. They were occupying niches that the dinosaurs just couldn't really fit into yet. And so, who knows, without the Triassic mass extinction, the dinosaurs may have just died off because they couldn't compete with the amphibians and other reptiles of the Triassic. But the extinction happened, and the dinosaurs not only survived, but yeah, they outpaced everything else. They just exploded in diversity. And that extinction was caused probably by the splitting of Pangaea. If you remember, all the continents, all the landmass of Earth used to be together in one supercontinent called Pangaea. And when that started to split apart, there's lots of volcanism, and that changed the atmosphere and led to a lot of global catastrophes. And somehow the dinosaurs were able to survive that. We don't know why. It'd be really cool to figure out why, but they did, and going to the Jurassic, they kind of took over. Now, mass extinctions, and just extinctions in general too, because animals go extinct all the time on their own. It doesn't have to be a mass extinction. It doesn't have to be a global catastrophe. Sometimes animal lineages just die off. They're outcompeted. Perhaps they're preyed upon to extinction. But sometimes animals just disappear. And this is actually really helpful for geologists, because that's how, largely, we split up geologic time. You hear about geologic time, we split it into eons and ages and epochs and periods, and there's lots and lots of stuff to know when it comes to geologic time. Just look at geologic time scale. But, you know, by and large, you have your Cenozoic, Mesozoic, your Paleozoic, Precambrian, all that stuff. We split it up into different levels. And each of those different separations, like, for example, in the Mesozoic, we have the Triassic, Jurassic, Cretaceous, and each of those can be split even further. We've got the Tithonian and the Maastrichtian and stuff for the... We split things into so many different time periods. And the way we do that is through index fossils. And index fossils are animals that we find and we can identify in the rock layer, and we say, okay, so I found this fossil at this spot in the rock layer, and oh look, there's another one down there. So this is all kind of the same time period. And then you can track that fossil through different layers, and then when it disappears, when it's gone, geologists like to use this as a marker for a transition into a new time. Let's take trilobites, for example. These are pretty common fossils, and there are tons of different species. But certain species of trilobites are excellent index fossils for the Cambrian. We can see a species arise, and then when we no longer see that species in the rock layer, that's how we can kind of divvy up our geologic time. You hear about people talking about geologic time, and it's not as if there was set blocks of time that just were divided by some kind of event. We divvied up geologic time. We know the Earth is 4.56 billion years old, and so as we're working on paleontology or geology, we use index fossils to try and organize this time into little segments that we can study piece by piece, right? And so that's why mass extinctions are so useful, because when there's a large amount of animals that die off, it's like, oh, there's a cut right there. There's a transition from one time to another time. We can see that, and that's really good. And in the case of mass extinctions, unlike individual species extinctions, is they really do have the potential to change the world quite a bit. So, the extinction of the dinosaurs. The dinosaurs reigned for millions of years. They were super successful. You might have heard people say that dinosaurs were evolutionary dead ends. That could not be further from the truth. They were massively successful from the mid-Triassic all the way to the Cretaceous. They occupied a period of time many magnitudes greater than our species has been around. As we talked about earlier, it wasn't until the Jurassic that dinosaurs really started to take over the world. And they started to diversify into a bunch of different groups and families. The Jurassic is when we start seeing some of the most classic dinosaurs are sauropods, such as Brachiosaurus or Apatosaurus or Brontosaurus. We also diversified into like our Stegosaurus, our Allosaurus stuff. Going into the Cretaceous, we saw dinosaurs reaching a peak of evolutionary awesomeness, for lack of a better word. Dinosaurs were at the top of their game, and then they vanished. Poof, they were gone. At the end of the Mesozoic, 66 million years ago, the dinosaurs disappeared. And after they died off, the mammals rose to become the dominant animals of the planet. And they still are to this day. So, the question a lot of people had was, why did the dinosaurs die off? And for a long time, the best explanation was, well, they were just evolutionary dead ends. Kind of in the early days of paleontology, before we knew that dinosaurs were actually incredibly advanced, incredibly diverse, and really at the top of their game before they died. Certain lineages, of course. Well, it's kind of hard to see extinctions in the geologic record sometimes. Sometimes an extinction is just triggered by biological or ecological factors that don't necessarily present themselves readily. Sometimes you have to dig. And so a lot of people figured that the answer to the dinosaurs' extinction would be in the rock layers. You study the fossils, maybe find evidence of disease, or study fossilized plants and find evidence of an ecological disaster. Perhaps a lot of plants died off, and the herbivores had nothing to eat, and then the carnivores had nothing to eat. But a lot more than just the dinosaurs died out at the end of the Mesozoic. We also lost a lot of marine reptiles. We lost a lot of invertebrates, such as ammonites went extinct at that time. Tons and tons of different lineages all went extinct at this time. So that kind of hinted at a global disaster. And there were several different theories put forth, but the one that you're probably most familiar with is the asteroid impact theory. And that's a theory that I think holds the most water, and a lot of people do as well. There are some people who say the asteroid was just a coincidence, that when it hit, the dinosaurs were already on a decline because of eruptions in India and the Deccan Traps. However, I think that the asteroid impact really was more than just a nail in the coffin. It was probably a catalyst. So, before I go into that a little bit, as I said, I wrote a paper on this. And so as part of my research, I actually went and visited a place that has a lot of clues as to why we think an asteroid killed the dinosaurs. So I'm going to play a quick clip that I took at that location. And I probably was a little bit, I was out in the field. So watch that, and then we'll come back here and I'll kind of fill in some of the gaps.
Hey guys, I've got something really neat to show you today. So, this little rock wall behind me may seem pretty unassuming, but it's actually incredibly important to geologists and paleontologists and frankly just science in general. So, I'm in Raton, New Mexico, and what we're looking at here is a transition from the Cretaceous to the Paleogene. So this ended the Mesozoic era, this began the Cenozoic era. Dinosaurs? No more dinosaurs. And the reason why is right here. I zoom in on that. You see that little white and kind of reddish looking stuff? That is what people call the boundary clay layer, the KPG boundary layer. It marks the transition from Cretaceous to Paleogene. So, this layer was first observed in the 1970s. We call this the Iridium anomaly. So, back in the 1970s, a geologist named Walter Alvarez, one of my personal scientific heroes, was in Gubbio, Italy. He was there to study paleomagnetic minerals and track tectonic activity through Earth's history. However, as he was in Gubbio, he came across this outcrop that had Cretaceous limestone and then Paleogene limestone. And he noticed something interesting. The Cretaceous limestone had just tons and tons of forams and other small marine animals. Tons of fossils, different species, hundreds and hundreds of them. The Paleogene limestone above that had very few. So at this point, the extinction of the dinosaurs was pretty well known as far as when it happened. The boundary between the Cretaceous and, at the time, is called the Tertiary. That term isn't used very widely anymore. But the boundary between those two layers was well known. And so he knew that an extinction event had occurred between these two rock layers. And he thought to himself, well, maybe whatever affected the biodiversity of these forams also killed the dinosaurs. So he looked closer, and what he found was a thin layer of clay. And that is kind of what we're looking at right here. You can see it right in there. And so he reasoned that this clay had something to do with the extinction of the dinosaurs and the end of the Mesozoic era. He thought that he would find clues in there. So he contacted his dad, Nobel Prize-winning physicist Luis Alvarez, and together they devised a method to analyze this clay with. They decided they were going to analyze it for concentrations of platinum group metals, like iridium. The reasoning behind this was iridium is incredibly rare on Earth's surface. Most continental crust around the entire planet has about 0.04 parts per billion iridium. And this is because iridium, being a heavy metal and also a highly siderophile element, is mostly concentrated in our core. During planetary differentiation, siderophile elements migrate towards the core. As you know, our core is mostly iron and nickel and other highly siderophile elements. And our crust is very rich in what we call lithophiles, things like our silicates. And so, even though iridium is super rare on Earth, it is very common in space. And the reason for this is because during the beginning of our galaxy, our universe, as elements are being created, as stars are dying, they have to go somewhere, right? And so they just go out into space. And so we have tons and tons of iridium floating around in space. Sometimes cosmic dust, we'll call it, blows across Earth's surface. And it leaves a little bit of iridium and these other heavy platinum group elements on the surface. And so the Alvarezes thought that, okay, if we analyze this layer and there are massive amounts of iridium, it means that this layer was deposited over a long period of time. It was exposed at the surface for a while. It was allowed to accumulate more of this cosmic dust. If it has very little iridium, it was deposited and then buried very quickly. So they analyzed it, and what they found was a crap ton of iridium. A lot of iridium. More iridium than they were ever expecting. So much iridium that it would have taken hundreds of millions of years for this layer to accumulate that much. And we know there's not 100 million years between the Cretaceous and the Paleogene. And so they thought maybe we have an anomaly. Maybe a mistake was made. So they went and they measured, they found another layer in Spain. They measured it. The same insane concentrations through the roof. And so they decided, you know what? This is an anomaly. There is a ton of iridium preserved between the Cretaceous and the Paleogene. And so the theory that they proposed was that an asteroid from space hit Earth, and when it exploded, because most asteroids explode into tiny pieces when they hit Earth, it enriched the entire planet in iridium and other cosmic elements. And yeah, in my opinion, to this day, this is the best explanation for the extinction of the dinosaurs. There are people who have argued that the iridium concentrations are due in part to eruptions in India, the Deccan traps, because some of their basalts have measured with a little bit higher iridium concentrations than other basalts. That's a whole other can of beans. I've got thoughts on that too. But as far as this goes, I think this is an asteroid impact at the end of the Cretaceous definitely happened. And we know it did because we found the crater. The Chicxulub crater on the Yucatan Peninsula in Mexico has been dated to 66 million years ago. Right at the end of this guy here. And so, you know, look, we've got a meteor from that time period, but through analysis of cores taken from this crater, we were able to link these iridium concentrations to that asteroid. In particular, this asteroid is probably what we call a C1 or a CI chondrite. These are big space rocks that formed very early in the history of our galaxy. And they actually have the same chemical compositions as the solar system, as our sun. Minus things like helium, hydrogen, the other noble gases. Those things, you know, they blow away. They don't like to stick around. They're too noble. They go away. But high amounts of iridium, osmium, all these other platinum group metals, platinum, and so yeah, that's how we got this. And it's so cool to be here looking at this. It's a pretty unassuming little formation. I keep hitting my head on that stick, but it's so vitally important. And to this day, this clay layer has been found all over the world in over 300 different localities. So it's a very well-documented event. It's a very well-documented anomaly. And yeah, it's just super, super cool. And as a big nerd myself, being here and looking at the actual rocks is astonishing. I came out here because I actually wrote a paper on exactly this, the extinction of the dinosaurs and the geochemical tracers that we can use to relate it back to an asteroid. And yeah, really, really awesome. Thin layer of clay with tons and tons of iridium. Around the world, the enrichments measure anywhere between 0.8 and 15 parts per billion. So if you compare that to average continental crust of 0.04 parts per billion, if you have even just an enrichment of 1 part per billion, that's astronomical. That's huge. And 15 parts per billion is insane. It's insane. So, yeah, just wanted to share a little bit. I know this has been a pretty long little video, but very, very cool stuff. Gotta love it.
Alrighty, so in that clip, I was pretty excited, so I probably didn't explain things as well as I could have, but you get the general idea. So you heard me mention in that clip highly siderophile elements and lithophile elements, and what the heck does that mean? Well, those are geochemical terms. So back in the 50s, there was this brilliant guy named Goldsmith, who was kind of the father of modern geochemistry. And he took the periodic table and he divided it into different segments based on how these elements behaved in a melt, a magma melt. And so there's 4 different classifications. An atmophile, which include things like the noble gases. These elements they just escape. They go to the atmosphere. Bye-bye. They don't like to bond with anything. They're very finicky about, what they do. They fly away. The second group is lithophile elements. And these are elements that are concentrated in the crust. These things like to be with silica-rich melts. Next is chalcophile elements, and these partition, is the correct term, they partition themselves into sulfide melts. And then siderophile elements, they partition themselves into iron-rich melts. So that's why we have so much iridium and stuff in our core and not very much on the surface. When our planet first formed, remember billions of years ago, it was all kind of a jumbled mess at first. But then, as time went on, it started to differentiate. We call this planetary differentiation. And so these elements start to partition themselves into the different areas that they are most comfortable with, the things that they can bond with easily, things that they're more attracted to. And so our core was formed with iron and nickel. And so all types of siderophile elements would obviously go there. Our iridium, our osmium, our platinum, all that stuff goes to our core. And then we have the mantle, of course, and then we have the crust and our atmosphere. And so the different elements partition themselves where they fit most comfortably. And so that's why the Alvarezes thought that they could analyze iridium in the iridium layer, because we don't have a lot of it on our surface, because most of it's in our core. Again, not everything, well, I didn't say this yet, so not again, but not everything in nature is 100% efficient. So even if you have 100 bits of iridium and you toss it into a planet that's differentiating, 99 parts will go to the core, and then you'll have that 1 bit that's in the crust. So nothing in nature is 100% efficient, but you get the idea. So when they found that there was a ton of iridium in this layer, they needed a source for it, and that's where chondrites come into play. So as we know, elements are formed in stars. Stars are basically just big element building factories. And as a star reaches the end of its life, a lot of things start to change. It goes from hydrogen fusion to helium fusion, and it starts shrinking. It starts getting close to imploding on itself, going supernova. And it also changes the type of elements that it makes. And this goes into nucleosynthesis and things like that. We're not going to touch on that right now. All you need to know is that elements like iridium are being made, and then when this star goes supernova, those elements are still there in space. And so that's why space has a higher concentration of those things than the surface of the Earth. And now chondrites, these are stony meteorites that formed at the beginning, or the C1 chondrites. They formed kind of towards the early days of our universe. And they never reached a size big enough to begin differentiating into planets. And so they stayed all jumbled up. And as mentioned earlier, they have a chemical composition very similar to that of the solar system itself, to that of a star. So they leave distinct impressions. They're pretty rare. They don't often hit Earth, but we do know what their chemical signature is. So, elements that are rare on Earth's crust are excellent geochemical tracers. You find that, and especially highly siderophile elements. These are siderophile elements that are extremely particular about where they partition. These elements make excellent tracers. If you find that, you know how it behaves. You know where it wants to be, and you know what processes lead to that element being there. And so you can trace it a lot easier than elements like lithophiles that can oftentimes have, they can bond with a bunch of different stuff, have a bunch of like garbage can minerals and things like that. So, the Alvarezes proposed the asteroid theory, and it was met with a little bit of criticism, but people were finding the iridium layer exposed all over the world, and yeah, it's tiny. It's just a few centimeters thick. They're finding it exposed all over the world. And for comparison, average continental crust contains 0.04 parts per billion iridium. Some of these iridium anomaly layers, they average anywhere from 0.8 parts per billion to 56 parts per billion. That is an absolutely astronomical enrichment. So, this theory was proposed, and it was meeting some criticism, but again, people were finding all these layers all over the world. And so finally, a crater was found. The Chicxulub crater on the Yucatan Peninsula. This was a crater formed by an asteroid hitting Earth that was probably the size of Mount Everest. We're talking between 6 and 10 kilometers in size. It was massive, moving at just absolutely insane speeds. And when it hit Earth, it left a mark. It probably traveled several kilometers into the mantle. It was a catastrophic event. It's the kind of event that would absolutely change the planet. So the Chicxulub crater, it's big. It's about 180 kilometers across. And it was dated to be 66 million years old. Well, that's when the dinosaurs went extinct. So right now, oh look, we have this huge crater that matches the date of this iridium layer. You know, there's already some correlation there. And then it would take a while for actual research to be done on the crater, surprisingly. There's a really excellent paper written by Goderis et al. From 2021 that I will link down below. Fantastic paper. Basically, what it's about is analyzing some core samples that were taken by the International Ocean Drilling Program and the International Continental Scientific Drilling Program that were taken from the crater. And these cores show, well, they preserve the impact and immediately after the impact. And so by studying these craters, these cores taken from the crater, it's become abundantly clear that we can, in fact, link the iridium anomaly to an asteroid impact, specifically the one at Chicxulub. So, the cores themselves, they contain, well, they show where the asteroid punched through basement rock, and they show that there was these huge tsunamis, lots of turmoil right after the impact, probably for a long, long time. And then we have limestone laid down that has, and this is the part that blows me away, fossils in it. Probably just a handful of decades, maybe a century after the impact, showing that life was making a pretty quick recovery. And that's pretty awesome if you ask me. Of course, those layers were analyzed for iridium and osmium, these other things that we would expect to see in a rock from space. And they were all compared against pieces of known chondrites that we have and analyzed for, you know, what type of rock did this? Could it have enriched the Earth this much in iridium? And the answer by and large is yes, absolutely. When this asteroid hit, a lot happened. A lot. The atmosphere was changed. I mean, the climates around the world were changed. And when this asteroid hit, it burst into pieces. And of course, again, it went a little bit into the, quite a ways into the mantle. But this huge event that caused all these tsunamis also have released a lot of particles of that asteroid into the atmosphere. And so you can think, after the impact, we've got iridium just going all around the planet. The air is choked with this stuff. Dust, debris from this impact, and a lot of it has iridium in it. And it's all, eventually, things start to calm down, and that iridium can be deposited on the surface. And so that's how we know that an asteroid hit 66 million years ago. That's something that we all know. You know, no one's arguing that an asteroid didn't hit. Whether or not it killed the dinosaurs, there's a little bit of debate. Personally, I mean, that's a pretty terrible catastrophe, and I'm pretty sure that that killed the dinosaurs, the mosasaurs, plesiosaurs, pliosaurs. I'm pretty sure that was a cataclysmic apocalypse, to say the least. Anyways, I hope this video was interesting. Again, I'll probably get better at doing these types of videos as I progress and keep practicing making these videos. But yeah, let me know what you thought. I tried to keep it as simple as I could. I'll probably do some editing, maybe add in some more information via text and stuff. But yeah, let me know what you thought. And if you liked the video, leave it a like, comment below, and subscribe. I've been Gideon. I'll see you in the next one. Adios.